Hello, I am Tim. In this video, I would like to introduce our recent paper, Verbalized Machine Learning. This is a joint work with Robert Bamler, Bernhard Schölkopf, and Weiyang. We start by answering the question, can we use natural language to parameterize functions? Let's use image classification as an example. Say we want to classify apples and bananas. In the usual machine learning setting, we can use a neural network to approximate the classification function f, which is parameterized in the numerical space using matrices. We can also use natural language to parameterize a function as long as we have an inference engine that can evaluate such a function. For example, in this task, we can use the sentence output digit 1 if the input image contains a round object, otherwise output 0. It is obvious that a human can evaluate this natural language parameterized functions and solve this classification task. Another inference engine that can understand natural language is large language model. This screenshot shows an example that ChatGPT is able to solve the task. We now know we can parameterize functions with natural language. The more interesting and important question is how to find the beta star so that the function can solve a given task. This is a task of learning. In the usual numerical machine learning setting, we are given the training data and try to learn and approximate the underlying target function g by finding the theta star. The common gradient-based learning algorithm mainly contains two steps: the forward pass to predict y-hats using the current parameter, and the backward pass to update the parameter using the gradient information. In our proposed framework Verbalized Machine Learning, VML, the goal, the data, and the algorithm are the same as in usual machine learning. The only difference is that instead of using numerical space for the model and the optimizer, we use natural language space in VML. In other words, the two steps, the forward pass and the backward pass, are now two LLM calls. Let's have a look of the detail for these two calls. This slide shows an exact text we used in the forward pass in the regression task. It contains a block for model parameters highlighted in blue, which will be replaced after each optimization step. A block for input highlighted in red. It will be changed for different input data point. And some formatting instructions such as the LLM has to reply with a block of explanations and the output. The output has to be real number rounded to 2 decimal. We copy and paste this, throw it to ChatGPT. We will get a reply like something like this: a block of explanations, a section of the output. We pass the output using regular expression to get the y-hat. After forward pass 1 millibatch of data, we need to do a backward pass to optimize and update the model parameter. This line shows the exact text we use in the experiment. It contains a block of input data, X for the current batch in text format, a block of current parameters, a block of predicted y-hats for the current input also using the current parameters, a block of the ground truth target y, a description of the optimization objective, such as the new pattern description should better predict target output, and also some formatting instruction. Copy paste to ChatGPT, we will get a response like this, which contains a session of reasoning, a session of the new model parameter. Similarly, we pass this text and extract the paragraph of new pattern description as the new model parameter and use it for the next batch of training data in the new training step. Overall, the VML algorithm calls the LLMs by alternating the two different prompt templates and extracting them, replacing the corresponding block of text in the template to effectively achieve learning in natural language space. Here is an example of VML for task of polynomial regression. The blue dots are the training data. We initialize the model parameter θ0 as the description of the regression tasks. Then we plot the current model by evaluating current parameter on the on an evenly spaced set of x to get the corresponding y hat. By passing the y hat from the text and convert them to float number, we can plot the result, which is the purple line, and it is rather wiggly at the moment. We can also calculate the mean square error and plot the training loss. Note that the training loss is evaluated analytically for the logging purpose only. It will not be fed into the optimizer as we saw from the prompt template before. After a batch of forward pass, we use the optimizer prompt to send an LLM calls for a backward pass. The optimizer outputs the text in the figure. It says, upon closer inspection, I noticed the input and target output seem to have positive correlation. I will use a simple linear relation between the input and output. The new model parameters is the sentence highlighted in blue. The optimizer here is essentially doing model selection. Using the new parameter, we can re-evaluate the model and replot the predictive function, which is now a straight line corresponding to the linear function in the model parameter text. After another training step, the optimizer output, I also noticed the target output seems to have a non-linear relationship with the input. I'll introduce a new pattern that captures the non-linear relationship. I will use a projective relation between the input and output. The updated model parameter now becomes a description of a projective function. We can see from the reasoning of the optimizer that it is still doing model selection, which changes the model from a model class from linear to projective. Again, we can re-evaluate the model and replot the predictive function using the new parameter, which is now a curve that corresponds to the projective function in the text. This time, the optimizer outputs the pattern seems to be undershooting the target input. I will increase the coefficient of the quadratic term to capture the stronger curvature of the relation. The updated model parameter is still a description of quadratic function, but with different sets of coefficients. We can see that the optimizer now switches from model selections to coefficient fitting. Using the new parameter to re-evaluate the model, we can see the curve now fits nicely to the training data, and the training loss drops to a new minimum. If we keep training for a few more steps, the training loss will continue to decrease and end up very close to zero. If we have a multimodal LLM that supports vision inputs such as GPT-4o, we can use VML for vision tasks. Here is an example of medical image classification. This is a pneumonia X-ray image binary classification task. Visually, without any medical training, it is quite hard to tell the difference between the two classes of images. We tried out two different initialization in this setting to include or exclude prior knowledge when initializing the model. This line shows the result without adding a prior. The model is initialized with only the definition of binary classification task. After training for 50 steps, the test performance can reach 74% accuracy. The resulting learned model parameters is a decision tree based on general visual features such as texture, symmetry, opacity. We can also inject prior knowledge about the data into the model using natural language. For example, we can append a sentence to the initial model parameter saying that the input is an X-ray image for identifying pneumonia. We can see that the trained model reaches higher text performance. And the learned model parameter now focuses on features that are related to medical symptoms such as inflammation, lung field, localized fluid. The learned model in this case can be verified by a trained medical professional. We can also imagine that VML can extract new interpretable knowledge from unseen diseases. In summary, there are three advantages of verbalized machine learning. First, it allows easy encoding of inductive bias, which is just a sentence in natural language. Second, it can do automatic model selections. And third, the optimization is fully interpretable in natural language, as it provides explanations for why an update is performed. Thank you for your time. If you find our work interesting, please check out the paper or reach out to us. Thanks.